Alright, we are recording, and first things first, Flame Nebula, NGC 2024. It's actually a Spitzer image, though I'm pretty sure that they did add in some of the Chandra X-ray Observatory data as well, so yeah. But it still seemed kind of appropriate for this, using a nebula instead of what I have been using for the other manufacturing related videos here. And this one's going to be a little different from those, because in the other two manufacturing videos, I talk about basically just my own reason, my own logic. This one is going to be more on the actual science, because something occurred to me a week or two ago, I think now, that's like, wait a minute. In various pieces of science fiction, they're doing things that's like, that actually doesn't work. So yeah, and I do have notes. Let's see if I can actually try to keep to them. So yeah, as the title does suggest, having to do with materials. Because, something that you do certainly see in plenty of science fiction is new materials. Like, Star Trek has titanium, Stargate has naquadah, and they also have trinium, and no other new materials are coming to mind. But those in particular are very, very interesting, because they are both described in the universe as being elements. And it's like, alright, well, here, let's look at periodic table. Okay, so this is periodic table of elements. And, give me just one moment. I want to pull up my original so it's a little easier to see. There we go. Yeah, so this is just pulled the data and made my own. But as you can see, I've got the different groups in here, the different classes in here, and this is, to my knowledge, up to date. Now, this is basically complete. In theory, we have up to 118, and it's actually named. I don't remember the name, but it is actually named. In theory, there could be a 119, 120, and so on. They would just, because of how the periodic table works, they would go down to underneath Francium, which is 87. And I don't remember what RA is, but 88. They would go down there, because periodic table has these patterns to it. That was a major discovery by Mendeleev, however long ago that was now. And actually other people had noticed that there were patterns within the elements as well, but he's the one who really came up with what we now would recognize as periodic table. And it was just, hey, he noticed these certain patterns in there, so we were actually able to predict, and he did make some of these predictions for elements in certain spots, because, hey, we skipped over one where it's like, I'm just trying to think what might be a good example. Well, here, if you found going from fluorine, and they would have, I think neon is really old, but if they had found fluorine and sodium, but not found neon yet, they should have known that, hey, there should actually be a gas in between these, a noble gas, neon. So anyway, let me try to get back on here. But yeah, it's still, the periodic table is kind of filled, and it's like we know the patterns in there. So when they start talking about how, hey, we found titanium, hey, we found trinium, hey, we found naquadah, it would have to fit somewhere on here. Which is kind of a problem. Hey, I'm just making sure. Okay, just reviewing my notes. Yeah, the problem actually comes about from, well, partly here. Let me actually, couple of things here to mention. Well, one will go with the other, but anyway, lead. So that's 82, it's PB, is the heaviest stable element that we've yet discovered any of that. Everything heavier than lead is, there are no stable isotopes. They are radioactive, they will decay. It's just how fast. So for example, uranium, which I will talk about more in a moment, that actually does have multiple stable elements. Well, not stable, and not elements. Multiple mostly stable isotopes, so they can last for millions, even billions of years. So that's going to be relevant here, because I'm just my copy over, and then there. So this is a variant of the periodic table where I now have it colored based on the dominant source of the element. Now some of these are made by multiple methods, but yeah, so we've got from the Big Bang, that would primarily be hydrogen and helium, some lithium, but for the most part that comes from dying low mass stars, as it says there. We've got cosmic ray fission, which I will explain, because that one actually I wasn't familiar with when I was looking this up. Type 2 supernova, which in theory I'm not sure what kind of supernova produced this, but I believe it was one of those. So that's a core collapse supernova, very big and powerful. Type 1A supernova, which is a white dwarf, where that's the now cooling core of a star, and just enough mass has fallen on it, likely from a companion star, that fusion reignites, and it actually will usually destroy the white dwarf. Neutron star merger, which definitely going to be talking about, and then man-made. So yeah, we've got basically from 95 on, that's Americium is 95 and on, the all man-made, but we also have Technetium at 43 and Promethium at 61. That these are basically only man-made. It was a little interesting because I've typically seen that uranium is the last element that is actually naturally made, but I was seeing some stuff saying that Neptunium 93 and Plutonium 94 are also natural. I think what it is that I mainly looked at plutonium for this. Plutonium has like only one isotope that lasts for a very long period of time. Uranium has multiple, so that may be why it's like, yeah, we don't so much count plutonium, because for the most part that just decays away and doesn't survive from a neutron star merger to actually settling on a planet. So okay, why am I talking about these origins though? Why am I doing that? Because where are you going to get any of those science fiction elements? We have from 95 on, they're all man-made, which means they're made in very small amounts, and typically they only last milliseconds. And it's also worth noting that it's like a neutron star merger. There are not many other events as high energy as those that also provide the material necessary for fusion. And even then, it's technically not even fusion. Okay, it was actually very interesting to read through this, and I'll hopefully remember, I'll put in one of the links that I used that actually gave various explanations. But yeah, so a neutron star merger and the dying low mass stars both are able to do something really neat. So the way the elements work is you have in the nucleus, you have protons and neutrons. Protons determine what the actual element is. So it doesn't matter the number of neutrons. If you have only one proton, it's a hydrogen atom. If you have two, it's helium, and so on. Well, what can happen with the low mass dying stars and neutron star mergers is you end up dumping so many neutrons onto a nucleus that it's unstable, and they will actually undergo what's called beta decay. Electrons are, beta rays are also electrons. So beta ray emission means you're shooting out an electron. Where's that coming from? A neutron splitting into an electron and a proton. Because neutron, it has no charge. Technically does, but it's very small. But it basically has no charge, so to keep things balanced, negatively charge the electron there, most of the mass becomes a proton, positively charged. Yeah, so that's how that works. And it's actually really interesting. We're basically making a very heavy, unstable element that has a low proton count, but by that decay, it becomes a different element. And yeah, both dying low mass stars and neutron star mergers can do this by different methods. And that's why you see dying low mass stars actually like all over. I mean, think about it. You've got lithium, carbon, nitrogen. That makes sense. But then why do you now have, I don't remember if that's strontium or not for 38, but yttrium, zirconium, don't remember, Nb. It's been a while since I really studied all this stuff, but molybdenum is 42, 50 is tin, tellurium is 52. Sorry, tin is 50. I think I may have said 52. 80, that's mercury. Thallium is 81, and then lead is 82. Those are made by what's called the S process, the slow process, because dying low mass stars, same thing where you're seeing those neutrons build up, but it happens over a long period of time. Neutron star mergers will do what's called the R process, which is rapid. So it's a whole bunch that get on there really fast, and so that does make some sense for why that launches up to such heavy elements, such that you would get uranium and potentially some plutonium, but yeah, I already talked about that. And then the Type 2 supernova, which core collapse, that's the supernova of a really big star. Why do those not go so high? Because you don't have the neutrons there. So that's more just the traditional nuclear fusion of just elements, the nuclei elements slamming together versus one nucleus that keeps getting more and more neutrons. That's what dying low mass and neutron stars with. And I know I'm definitely off notes, and hopefully I'm accurate on that, because some of this I really needed to read to make sure I understood all of it, and so I may have some of that science wrong, but I don't think I'm that far away. Oh yeah, I forgot to explain the cosmic ray fission, which is actually pretty neat. So that's basically elements like beryllium and boron, which are both colored for that. They would be made from what it looked like. They are made in the core of a star, so they technically are a dying low mass star because it is also like for lithium, carbon, and nitrogen. They are still made there, and then when the star dies, it sheds that material. But it's not by the S process I was talking about that gets you the heavier ones. But for making carbon and nitrogen, they're burning the beryllium and boron. So what's happening to make the beryllium and boron is when the star dies, there is a massive explosion, but it lets that out, and it then creates these cosmic rays that hit the carbon and nitrogen atoms or heavier atoms, and causes them to undergo fission, producing the beryllium and boron. It's actually kind of neat. Where they are components to make it, but get burned through very efficiently, and then it's at the end, the final product is actually destroyed to recreate them. So it's kind of neat that. So okay, trying to get back on task, back focused on this. So I already mentioned how we don't really have a place that these elements would fit in, unless it is that some of the man-made elements are what we're talking about. That maybe titanium is supposed to be 112. Maybe naquita is supposed to be 116. Maybe, but that still is though only man-made in very small quantities. Now there is something that might change this a little bit. That's the so-called island of stability. So the idea here is, I was talking about protons and neutrons. The number of both influences the stability of the nucleus. And they actually have a chart that graphs the number of protons versus, I think it's actually the combined number of protons and neutrons. It might just be of neutrons. But they do that, and then they plot out as well what the stability of them is. So if it's very stable, if it is stable as in it can last 1 billion years, stable as it can last 1 million years, 1,000 years, 100 years, 10 years, 1 year, and so on, going down to even just milliseconds, there's actually this funny thing where typically the heavier you get, so as you would go up, no, there we go. The flipping is always going to get me. As you go up the graph, and I couldn't figure out how to make my own version of the graph, and I don't want to just grab somebody else's. But if you look up island of stability, you will find it. But as you go up, basically the stability decreases. The heavier the nucleus, the more likely it is to be unstable. The island of stability is this weird spot where basically it was going down, the stability decreasing, but then it suddenly increases. So it's okay, maybe that's where these elements are. But the problem is that the island of stability is predicted to be around 114. It might actually be heavier, though. One thing that I was seeing is 114 for the number of protons. I don't remember what I was saying for the number of neutrons. Or 127 was another number that is considered, that might be one of these magic numbers, at least for protons, and was certainly not by 127 yet. So it's okay, so maybe, just maybe, we are talking about an element that is made by some unknown process, because we're talking something that would have to be at least, likely more, energy intensive than a neutron star merger. What's more than that? I mean, maybe a hypernova, but those are only theoretical. I guess, could a strange star do it? Strange stars are hypothetical objects that I don't think anyone has proven exist. It's basically, you got the neutron stars where things collapse down such that protons and electrons collided, forming neutrons, basically the reverse of the beta ray emission. Strange stars are even more compact, where now the neutrons themselves have decomposed into their parts, which are called quarks. Also, gluons would be in there. And they're called strange stars, not because they would be very strange, but also they sometimes quarks and gluons are referred to as strange matter. And it would basically just be a ball of that. And this would exist between a neutron star and a black hole, but it's one of those, I think it's just a hypothetical, the window that one would be made in is so tiny that it's very likely would never exist. Anyhow, and I don't know if you could, well, I guess you might have those quarks and gluons if they escaped it. Maybe they could cool down into protons and neutrons, but why would they cool down into super heavy elements? And not only that, unstable ones. Because from what I could tell, looking at the island of stability, they would still be unstable. They're just more stable. So they'd be like, well, anything past lead, like uranium, where there are isotopes of uranium that can last for billions of years, that they have a half-life of like 4 billion, I think one of them said. Okay, great. But it's still, they're not going to be made in large quantities, and a lot of it might be more like plutonium, where it's like, yes, there's one that lasts a really long time, everything else just decays away. So this idea of building a ship out of it, in the case of Star Trek with titanium, it's a radioactive element. Like, these aren't going to be stable. They will be radioactive elements. I don't think I'd want to make a ship out of that. And also, there should be very little quantity, so how are you actually making all that? And don't save replicators. Seriously. I mean, don't. Because, I mean, it's still, the energy has to come from somewhere. We're talking about something more intense than neutron star mergers, potentially, or just on par with a neutron star merger. No. I'm saying no. That's ridiculous. And then with Stargate, you've got Naquadah, which actually is described as being radioactive, but then I think they also described that ships are made out of this, so I got no idea what they're doing there. Maybe that's just maybe they're figuring, hey, there's a stable isotope and there's a radioactive isotope, and just they always use the same terminology, and they never, like, well, I guess trying to avoid giving the isotope number would be fair, because then you'd be settling things a bit too firmly. Don't know, at least they do have Naquadria that they do describe as a separate isotope, and that is way more radioactive, so anyhow. I do actually have a conclusion to this one written down. There's actually something kind of neat that I realized. So, my larger point here, and I know I've been rambling, some, only at about 16 minutes, so that's not too bad. I don't think it is reasonable, and now that I've thought this through, I haven't done it yet. Now that I've thought this through, I don't think I will ever introduce an element in my science fiction, just because there's no place for it, or its amount would be so low as to be unuseful, unless you're like going straight to mine a recently emerged neutron star event. I don't think I want to do that either, because that's still going to be a lot of radiation, a lot of heat. I wouldn't want to put any ships there. So it's like, yeah, I will never introduce new elements because they don't fit. And I don't know how you could reasonably say they were made. And it's also like all these man-made ones, with the exception of like some of the ones right by plutonium and such, would be made in very small quantities, like a few atoms that last for such a short period of time, we don't even observe them, we observe what they decay into, because we predict what they will decay into, and then we're like, hey, we did get that, so it must be we made the element that we couldn't actually see directly. So, while yeah, there's all that, on the other hand, it is still possible to have very advanced materials. I mean, some of the properties of titanium. Hang on just a second. I'm trying to. Okay, there. The properties of titanium, we could find a material that has those. The properties of Naquadah, except for the radioactive stuff. Well, for what the point I'm getting to for the radioactive stuff, we might not ever find, but the strength of tritium. Tritium is one in Stargate that isn't described as being radioactive. It's just a very strong material when purified. It is still possible that those we may find. They just won't be elements. They'll be alloys. And this is actually very reasonable. And I looked up, I tried to find the number of alloys for steel, which steel is itself an alloy, but there's alloys of steel. 350. About 350 of that, and I wouldn't be surprised if we continue to find more, either by just finding other mixes, or by getting more and more specific in the manufacture, because some steel alloys are going to be like other steel alloys, but they might be close enough that originally when we discovered that alloy, it's like, yeah, it's the same, but we've gotten so good at manufacturing one or the other that they've split, and who knows, maybe we'll find some in the middle. And that's just steel, which is iron and carbon. Steel is an alloy of iron. There might be other alloys of iron. We only know steel. I mean, everything is based on that. But you've also got aluminum that I'm pretty sure there are alloys of. Copper. Copper definitely, because it's brass and bronze. Titanium, I believe we have alloys of. And that's just a few. I'm just going to pull up this one. So it's like, I mean, there's a lot of elements here, a lot of metals here that could potentially, we just find alloys that may give us those science fiction properties, those science fiction materials And one neat thing about that is a lot of these exist on Earth. So it's actually like kind of this positive thing where it's like, yes, we can't have tritanium as a new element, but we could potentially make tritanium on Earth if it is an alloy. We might have all the components here to do. We just need to figure out how to make it. And similarly, composites. So something that would be more plastic or a variant of carbon, for example. There's a lot of focus on that with things like graphene, which is wild. Seriously, look up graphene. It's crazy. Because it's transparent, flexible, stronger than steel, highly conductive, and actually has something called Dirac cones. I mean, graphene is wild. It also can do one thing that's very weird. It actually will work as a barrier for helium. Helium gets through almost anything. Graphene will actually prevent it from getting through. But water can get through. It's very weird. It's very weird. But that's true. Somehow, the water molecules actually are able to align just right. In graphene looks like chicken wire. It'll align just right and be able to pass through. But helium will actually be blocked by it. It's crazy. And there's a lot of research being done on other allotropes, A-L-O-O trope, of carbon and other materials, where an allotrope it's like a pure carbon, but it's different structures. So like diamond and graphite are both allotropes of carbon because they're pure carbon, but different structures. And then graphene is in there, carbon nanotubes, nanoribbons, and there would be others. And there's also mentioned graphene. Yes, graphene. There's also like graphene. I mean, it's really, really neat. So there's plenty of science fiction materials yet to find, but it's more of we already have the ingredients. We need to figure out the recipe and then figure out what the properties are. And one other thing I want to add concerning that, and I'll leave the periodic table up for this. I'd seen this years ago. I haven't seen anything covering it since, which is disappointing. Because I lost access to a lot of the science news, but it was even years before losing that I didn't see anything. Researchers at different universities, but also drug companies working on libraries. They were referred to as drug libraries. They were way more than just libraries. These were, I would say, everybody's losing their minds about AI and machine learning today. That's what they were doing. The idea was that they would collect all the data like a library into a database, essentially, feed that into an AI, feed that into a machine learning algorithm that would go through and then be able to predict. Because if you say, hey, I need a medication that has these properties to it, that will produce these results in human physiology, and it'll spit out, hey, I think these will work, and I also, based on other similar molecules, but also say, and this is how I think we'll make them. This is how I think you can make them. It was really, really neat. I've seen nothing about it, and it was really disappointing. Hopefully they are continuing to work on that, because that would be such a renaissance. Because right now, the way drugs are made is basically, we take a guess. It's sort of a shotgun, and you hope it hits something that works, where you'll make like a dozen in a batch. And maybe if you're very lucky, you get one that's viable. And even then, the FDA may decide, no, we don't like it. And you have to throw it all out and start over. It's kind of a mess. But this would shortcut that a lot, because at least you'd have a better chance of having one that is correct. But potentially you could do that with alloys as well. I don't know how much with composites, because some of that with the structures, I could believe that would get too complex there. Well, even then, you do have some of that with alloys. I could see some alloys being simpler than to predict than composites. But anyway, yeah. So it is just materials are actually really interesting. They are. I don't know enough about them. I know enough to respect and appreciate material science. But yeah, it was just one of those things that, and now I can't watch Star Trek. My television's over here. I can't watch Star Trek. I can't watch Stargate. I don't know if there were new materials in Star Wars, at least any that I've talked about, but I don't know if I can watch any of those now and not be like, that's not a new element. It can't be. Anyway, see you next time.